Right guys, this week's session. We looked at capacitors last week and we just considered them charging up fully, and I talked a little bit about this transient period, i.e. the time when it's actually doing the charging from 0 up to its maximum, or the reverse of that, the discharge cycle. So that's what we're going to look at a little bit more closely this week, charge and discharge cycle of a capacitor. I want to talk a little bit about how we describe quantities when we're talking about transients in circuits. Okay, because when indicating transient values, uppercase, lowercase, lower case letters are used, e.g. lowercase v, and to complete it you would say the v at time t, yeah, transient voltage, so we're going to be looking at functions that will allow us to calculate the actual voltage at a time t seconds after switch on, for instance, or at time t seconds after closing the discharge switch. Yeah. We'll also be using a lowercase I at time t, perhaps not always include the t in brackets, but that would be the full version. That's the transient current, and both of those are at time t seconds after some event. Okay, in this case we'll be talking about after switch on or after closing any kind of discharge or connecting a discharge resistance. In these functions we'll also come across uppercase V, which is the applied voltage. We might actually use Vm for Vmax or something like that, because that's going to be in the function as well, the applied voltage or the capacitor voltage at the start of discharge. And Im, or an uppercase I, being the maximum or initial current, depending on whether we're looking at the charge or discharge cycle, but the uppercase letters are used for maximum values, and that follows all the way through electrical principles. So uppercase, we're talking about maximums. Lowercase, we're talking about an instantaneous value at time t. Okay? So first of all, capacitor charge. We're going to look at the charge cycle in steps from the time we switch on. Okay, so if we initially assume VC equals 0 volts, and that's a lowercase v. Yeah, so if we assume that the capacitor is absolutely and completely discharged and has 0 volts across it. So here's our circuit. C. We'll have a 10 volt DC supply and a series resistor R of let's say 10 ohms for the purposes of this. And for the purposes of this, that would be about 0.1 farad. It's a big old capacitor, but don't mind. Okay. So, with that circuit as it is, initially, how much voltage is said, how much voltage is across the capacitor. The initial state is that VC equals 0. So what's VR?
10 volts.
Yeah, why, Howard?
Because there's no voltage being drawn from the capacitor at the time. It's all going through the resistor.
Tell me the law that tells you that there's 10 volts across the resistor. And we're talking about at the instant this switch is turned on. What law tells you that's 10 volts? What are we working on? What way would I put a voltage arrow for the 10 volts?
Going to the right.
Yeah. So Kirchhoff's voltage law says that this voltage E is equal to those two added together. If that one's nothing, that one must be 10 volts. Yeah? Everyone agree? So I'm going to just extend the page a little bit and start to draw a graph. That's a time in t seconds. Okay, we're going to have on this scale we're going to have V, but we're going to have the current as well in a minute. Okay, so our voltage starts. Hang on, we want red is going to be VC. So VC starts at nothing. Green is VR. That starts at 10. Yeah. And then blue, I'm going to make I. So, how do we calculate how much current is flowing in that circuit? How do we calculate the instantaneous current at time at 0? I-O. How can we get that? What law would we normally use, and where can we get the information from? Yeah, Ohm's law. And where have we got two pieces of that information and not the current? With the
10 volts and 10 ohms.
yeah, if we can focus on just the resistor. It's got at the instant we turn on, it's got 10 volts across it. So it's 10 over the 10 ohms. 1 amp. Yeah? So I'm going to start the current slightly off. Remember, we're going to be working with different scales here a little bit on this, but I want to show them all on one graph. So that 1 amp at the start. Okay, everyone happy? This would be about 5 volts. And about there is going to be 0.5 of an amp. That gives me an idea how the scale is. So I want to try and draw it as accurately as I can. Okay? And I want about 1, 2, 3, 4, 5 seconds on that scale. Okay. Right. Now, if I copy that page, because I can do that, and we move on to about, let's say a second later. A second later, or a short period later, the capacitor voltage, not a second later, a short period later, the capacitor voltage is charged up to 1 volt. Yeah. What does that make now? The voltage across the resistor? 9 volts, because we can only have 10 in total. So that becomes 9 volts. I'm going to get rid of this and say after short period 3 seconds. Yeah. So we'll have charged our capacitor up to 1 volt. Therefore our resistor voltage will be 9 volts. And our current will be 9 volts divided by 10, 0.9 amps. Yep. So we're talking about, I'm going to stick a line in there for a minute, and I'll explain that line a bit later. Okay. So our capacitor voltage has gone down to about there. Sorry, our resistor voltage has gone down to about there. Our capacitor voltage is up in the same amount of time to about 1 volt. To be read, and the current after the same amount of time is down to 0.9 of an amp, about there somewhere. That should be blue. Okay, so we start a move. Okay, I'm not going to start drawing the curves in yet. We'll go a little bit further first, but that's after 1 short period of time. Okay, if we then go a similar period of time to that, I'm not going to do too many of these. We'll just draw it in eventually, probably after this one and the next one. Another short period of time, so a further short period of time. Let's double the distance. Let's go when VC has got to 3 volts. Yeah. What will VR be? 7 volts. And the current will be 7/10, 0.7 amps. Yeah. So after that amount of time, so we go on there, back here somewhere, the current will be 0.7. The resistor voltage will be 7 volts, back there somewhere, and the capacitor voltage will be 3 volts. About there somewhere. Okay. Now, what happens as that carries on is this goes down like so, and I'm being very careful that it doesn't draw that again. Don't draw that very well. Let's undo that for a minute. Have another go. Making it a definite point to show that it doesn't actually touch 0 in theory. Okay. The current goes in a similar direction, in a similar shape, and again doesn't hit 0. Okay. And draw a dotted line across there. VM, okay, the maximum voltage, 10 volts that we're applying, the capacitor voltage does that and doesn't quite get to 10 volts. If all we apply is 10 volts, it actually never gets quite to 10 volts in theory, but it gets so close that it doesn't make any difference. It gets to 99.99% of it eventually. Okay, depending on how much charging current we got. So they're the shapes of your 3 quantities here. This is VC. The blue one is I. And the green one is VR during charging. Okay. Let's take a version of this too. I want to focus now a little bit on this line, this dotted line I put in here. Initially. Yeah? And that's the initial. Hang on, I really want to focus on one that goes this way. What that is it's the initial slope of VC. From your maths, it is dVC by dt. rate of change of capacitor voltage with time, initially, right at switch on. Okay? Now, that, if we maintained 1 amp throughout the whole charge period, that's the rate at which the voltage would go up on the capacitor. So, if initial 1 amp is maintained, the rate of charge would remain constant. So the slope of the capacitor voltage wouldn't do that tailing off. It would remain at that rate. And if you kept on putting 1 amp in, it'd carry on rising at that rate and go beyond 10 volts. But because we're not allowing that, because we aren't keeping, because the current charging rate isn't staying steady, the rate at which the voltage across the capacitor isn't increasing at the same rate. Okay. Now, if we take that rate of change, if we take the point where it hits 10 volts, that slope, this time here is called time constant for that particular resistor, capacitor combination. So the time it takes with the same rate of current input to get to the 10 volts we're applying, that's where they define what's called the time constant for this circuit. Okay? And time constant and they use the Greek letter tau for the time constant is equal to C times R seconds. So we can choose what that time constant is by selecting a suitable combination of capacitor and series charge resistor. This cycle and the discharge cycle is very repeatable. You keep switching up, if you switch on, charge up, switch off and discharge, that process, the timings are very repeatable. So you find them used in charging circuits because it takes the same amount of time every time. And what you're going to be doing with your practical is using, in fact, the discharge cycle to help you work out what the value of an unknown capacitor is. Because you can repeat this thing and it's always the same. Okay? Now, the other thing is, rule of thumb, capacitor, although it doesn't ever get to the 10 volts, and you'll see that in your practicals, if you just apply exactly 10 volts it will never quite get there. Capacitor is considered fully charged after 5 time constants. i.e. 5 times C times R. Everyone happy with that? Yeah. So what we're going to do now is formulate the charge cycle. So VC at time t. What does VC do during the charge cycle? That's time. That's VC. It does that. We're also going to look at I at time t. We know that I over time does that. And then VR at time t also does similar shape to the current. Leave that one for a minute. What type of function give you that graph shape? What would you call that graph shape? These ones. Both those two. Any ideas?
Try to speak. Exponential.
Exponential
Decay.
decay. Yep, they're exponential decay. We find the current from Im, the maximum current, times e to the power of minus t over CR. What you'll find in all of these functions is this bit comes in all of them, and for a positive value of t, that is always worth a little bit. So it's always going to be, even down here, even after a long time, that's still going to be worth a little bit. So in theory, the current never fully stops flowing, because e to the power minus t of CR is always a little tiny bit. Right? So should seem reasonably obvious that VR goes like this. The maximum voltage times E, because it starts off high, to the minus T over CR. And again, this bit here, E to the minus T over CR, is always worth a little bit. And so this voltage actually, the resistor voltage is never fully zero, although it might be measurably zero, depending on how fine your meter can measure voltages. Okay. What about this one? What is that shape of graph called? Any ideas? Not very committal this morning, are we? Doesn't matter if you get it wrong. Anyone think it's exponential rise? No. Because exponential rise would be that. Carries on going forever. Very quickly. So not talking about that. What it's called is exponential rise to a limit. Yeah. So the limit being the maximum voltage. So VC is given by Vmax times 1 minus e to the minus t over CR. And because that bit, as we've said down here, the e to the minus t of a CR, even after a long time, is always worth a little bit. That bit in the brackets is always going to equate to something less than 1. And so in theory, the capacitor voltage never reaches Vm, ever. But it's considered to after 5 time constants. We'll find out how much charge that is. We do an example. Okay. So let's go back to our example circuit. We had 0.1 farads. We had 10 ohms. We had 10 volts. And we had a switch. Right. First of all, let's find CR. So this is what I'm going to do here is help you see some facts about the way this charge cycle goes. So if we find CR, that's equal to 0.1 times 10, 1 second. Yeah. Right. VC after 1 time constant. VC equals Vm 1 minus E to the minus T over CR. 1 time constant is 1 second, so if we put the numbers in, it's 10 times 1 minus E to the T is 1, so it's minus 1 over the time constant C times R is 1, so it's E to the power of minus 1, that is. Push the buttons on that and see what it is, please. Anyone got me an answer? 6.3. 6.3. .3 volts. As a percentage of what we're applying, 63%. Yeah. So it will always get to 63% of the. This is repeatable. We'll always get to 63% of what we're applying after 1 time constant. That's the repeatability of it. Okay, if I change those values, the voltage applied and the capacitor and the resistor value, it will still get to 63% of the applied voltage after 1 time constant. Okay, calculate now what VC is after 5 time constants, please. So after 5 time constants, although it's not 10 volts, it is as close as you're going to get to it, and therefore we consider the capacitor as fully charged. Okay? And in fact, if you've done every time constant, you'd find that for each time constant it gets 63% closer. So it closes the gap by another 63%. That gap's getting smaller and smaller all the time, but every time constant it does that. Okay? So we can also do the current. So I, after 1 time constant, I equals Im E to the minus 1, that would be, wouldn't it? Minus T over CR, which is 1 second. Okay. How do we get I maximum in this case? What is I max? Where does the maximum current flow in this circuit? When does the maximum current flow? When you switch it on, we got the whole 10 volts across the resistor. So the Im is always V over R, in this case 1 amp. So that is 1 times E to the minus 1. What's it going to be? Before you calculate it, what's it going to be? I reckon 3.37 of an amp. Ish. 0.37. It's lost 63% of its starting current. Yep. I got 6.3 on the brain, so
It's lost 63%.
yeah, like the voltage across the capacitor has climbed by 63%,
Yeah.
the current from its starting current has dropped by 63%. And if we'd done the same kind of calculation with the resistor voltage, we'd find that after one time constant, the resistor voltage would have dropped by 63% to 3.7 volts. Yeah?
Why is that 1 times T to the minus 1?
Because what it is
Why is it not over CR?
the formula is, sorry, I ought to put minus T over CR there. Okay? The time constant is 1 second, so that makes that minus 1 over 1, which is minus 1. But I agree, I shouldn't have put it on the formula, I should have put it like that. Alright? Yeah? Okay? Or not? What we're going to look at now is a kind of problem where we need to rearrange this formula. We're going to look at find the time when little VC is equal to 5 volts. Yeah? So we got a formula, little VC is equal to Vm times 1 minus E to the minus T over CR. Close brackets. We're going to look at rearranging that formula so that we get T equals something. Sure, you would probably have done that with Mr. Jackson, but where do we start with rearranging that formula to get T equals something?
Would you start by
Sorry?
Would you start by taking the voltage?
Yeah, we need to get rid of the voltage max because then the brackets can go, yeah? So what do? We divide by Vm. That gives us Vc over Vm is equal to 1 minus E to the minus T over CR. What would you do next? remembering that we don't really want any kind of minus t. We've got to get what we got to get rid of next. Yeah, we could do that. So, what we're going to end up with? We're going to take one from both sides, but then we're going to end up with a minus e to the minus t of a CR. So could be a little bit tricky. And I think
Would you log it so that the
if you
cancel out?
well, yeah, you could do that, but this is what I would do. I would, let's put this in a bubble here, plus e to the minus t of a CR on both sides. So I get that over that side and get rid of the negative symbol. So it's almost an extra step, but I think it makes it easier to understand. Plus e to the minus t of a CR is equal to 1. Yeah. Now I can add VC over VM to both. I can subtract VC over VM from both sides. To end up with e to the minus t over CR is equal to 1 minus VC over VM. Okay. How do I get rid of the e to the power of? And a good way of finding this out is to look at your calculator. What's the inverse? What's the other function on the e to the power of button? In ln, natural logarithm. Yeah? So the opposite of e to the power of x is ln x. So if we take the natural log of both sides, ln of both sides, if we do ln on that, we end up with minus t over CR. We're getting there now. We've got to do ln of 1 minus little VC over VM. How do I move the CR? Divide, so I've got to multiply. So I end up with minus t is equal to ln CR times ln 1 minus little VC over VM. And how do I get rid of the negative symbol in front of the t? Sorry?
Did you put it over 1?
No.
Would you make the answer minus?
Yeah. If you effectively multiply by minus 1. Multiply both sides by minus 1. Yeah. So all we do is say that t is equal to minus CR ln 1 minus little VC over VM. So, yes, it's a bit unwieldy, okay, but not particularly difficult if you take a step-by-step approach to it. Getting rid of the item outside the brackets first, then moving things around a bit. Think about what you want to end up with. Try not to end up with negative items on their own if you can. So think about moving something the other way instead. All right. And if we can now put our numbers in here, so we can go T is equal to minus CR. C times R is 1, because the time constant is 1 second. We multiply that by the natural log of 1 minus, we want to know when VC is 5 volts. So push the buttons on that and we should get the time when VC would be equal to 5 volts. What we got? 0.69 seconds. Would we expect it to be less than 1 time constant? Yes, we would, because we know after 1 time constant it's reached 6.3 volts. Yeah, and the time constant's 1 second. So you should know, and that's a good idea to know that, because then you'll know if you've gone wrong somewhere. You ought to know if you've gone wrong in terms of that. If we had more than a volt here, we'd know we'd gone wrong, more than a second here, we'd know we'd gone wrong somewhere, because 5 volts is under what we know it should be, 63% of the 10 volts after 1 time constant. Yeah, which is 1 second in this case. Okay, so that's the charge cycle.